Good afternoon, everyone. Thank you for joining. Let's see whether Erik is also already there.
I'll be there.
You are there. So thank you so much for joining us to this webinar. We hope you are really enjoying the MOOC that we have prepared. And yeah, in this webinar, you can ask us many questions, all the questions that you have, other things that you did not see yet, maybe in the MOOC. And if you are out of questions, we can have other interesting discussions. So are there people who have seen things that they have questions about? Not yet. Not yet. So maybe then Erik and I can, while you are thinking about all your questions, Erik and I can have a little introduction. You might have seen that already in the course description, but Erik is my boss. I am Erik's postdoc. I work at TU Delft. Erik also works at TU Delft. I did my master's in chemistry. I did it in Leiden University in the Netherlands. I specialized there in bioorganic synthesis, which is quite different from the things that I do at the moment. But it makes me an organic chemist, which I use a lot for the postdoc I'm currently working on. And during my last years here at TU Delft, I also became kind of familiar with electrochemistry. So I could call myself now a little bit an electrochemist, I would say. So Erik, maybe you can tell us about the path that brought you here.
Yeah, I hope people can hear me. Is that correct?
Yes.
Right. Well, as Mark said, my name is Erik Kelder. I'm associate professor at the TU Delft. My history is basically working on thin layer deposition techniques that I started in Utrecht University, where I graduated for my master, and I moved to TU Delft, do research on thin layer technologies for solar cell systems, but the materials also seems to be interesting for lithium-ion batteries. So I've been involved in lithium-ion batteries for quite some time, and in the meantime, I was writing EU proposals, and I was finally asked by a Danish company to join them. So I've been staying for a while in Denmark at the battery company where I wrote new proposals. So I came back also due to private reasons, good private reasons, because my wife became pregnant. So I came back to Delft, and since then I'm still working in Delft on battery technology, starting with lithium ion, and since short on zinc air battery and other redox flow systems.
Yeah, and that's also the project that I work on at the moment. Yeah, thank you for the introduction. Are there more people who want to introduce themselves? Because we saw in the map that you could fill in, we saw quite interesting stories from you, where you were from, what kind of careers you're having, whether you were a student or not. Oh, I see
Well, there is a
there's
chat. Yeah.
there's a chat. We have a question. We talked recently about storage technologies. What are your thoughts around a recent deployment of sodium ion for grid storage? And that other word I can, peak energy or the potential of vanadium flow. That's very interesting. That I find that super interesting. Maybe Erik,
Yeah,
you
I
can
can.
say something about this?
I can give an answer on that. Well, since sodium ion batteries and lithium ion batteries do not differ so much in the chemistry as such, except of course that you're working now with sodium ions shuttling back and forth rather than lithium ions, the materials that is in the cell is quite often the same. And what is most interesting is that the electrolyte today is mainly of organic origin. That means they're still inflammable. On the other hand, sodium as well as lithium might react with water and air. So as soon as one of these cells will be opened and exposed to air and moisture of the air, it can catch fire. So if you are talking about sodium ion for grid storage, that could be of interest due to the price, but it should not be in urban areas, because if you already see what might happen with small cells, and actually yesterday here in the Netherlands, we already had a fire due to a fat bike that catches fire due to whatever the reason is, and the whole apartment has to be evacuated by all the people, and that is just a small lithium-ion battery. And if this will be bigger, then you might expect some uh, difficulties with the people living around such a system. So it is dangerous probably in urban areas, but it doesn't mean we cannot use it. If it is in rural areas, then okay, maybe that is safe. But
Yeah,
the
the
other,
fat bike, that's actually a quite interesting story because they were just charging it. They were doing what they were supposed to do. They were just nicely charging it, and then it caught fire.
yeah, so it has nothing to do by misuse or whatever. It happens. So in that is a critical situation, and as you probably can understand, what happens after the tsunami in Japan, where the tsunami flooded completely the nuclear reactor there. Suddenly people realized if you have a fully safe system, you never know what the environment is doing. And that was exactly what happened there. It was a safe system, but once that accident happened, no one knows exactly what to do. So today it is more important to understand what are we going to do if such an accident happened, rather than to convince people that it is safe, because the accidents will anyhow happen. That is what we will see today.
Yeah, so by reducing the size of the batteries itself, so not for grid scale, but maybe for your electric bike, then in principle, not a whole neighborhood will burn down, maybe your own little house. And if you
Yeah,
catch it on time and you act well, you can make sure that it doesn't go towards your burning house. But so yeah, I agree fully with your thought on sodium ion. But then the vanadium flow battery becomes very interesting, right?
yeah, the system with the vanadium flow, that works, of course, in aqueous solutions. So that seems to be a little bit more safe, despite it has a lot of acids in it, very concentrated sulfuric acid or other acids. But nevertheless, it doesn't catching fire. So you do not have these dangerous fumes coming out of the system. So indeed, it is certainly an interesting potential for grid storage. The only question is, are we willing to pay the price for such a vanadium redox flow system? But since today it is expensive, and if an accident happens, then we have to realize vanadium itself in a solution might be poisonous.
Yeah, but you can handle that, right? If
Yeah.
you have like a leak safe building and it's an industrial site, you should be fine,
Mm.
right? Chemical industry knows how to handle these types of spills, I would say.
But this
But
is exactly why we try to do this whole MOOC, to understand you the issues related to the various systems. So we hope that all of you can create and find some interesting alternatives, or find some solutions to overcome the issues. So it is basically not up to Mark and me to define what is best or what is worth. No, we hope that you will come with the solution. That's why we do this MOOC.
but we also want to
Mm.
bring in some solutions, right? In the end.
Yeah, yeah, yeah,
Yeah.
yeah. But that's not the issue for the MOOC. That's
No.
our own research.
If you have questions, by the way, just let us know. You can also put in a little chat there. But yeah, so Eric and I work on an EU project which is called Resilient, and we want to make a zinc air redox flow battery. I think we already talked about it in module 2 somewhere. I always forget in which module stuff happens. But this is a battery type where we use zinc on one side, so it's solid zinc that reacts to zinc oxides because the battery is alkaline. And on the other side, we have an air electrode with a catalyst where you can do oxygen reduction and evolution. And then in principle, the reaction that you have is zinc plus oxygen becomes zinc oxide. And the reason why we are so excited about this system is because the chemicals involved are I wouldn't say safe to eat, but they are manageable. So from a toxicity standpoint, much better than redox flow vanadium. And from the flammability point of view, it is better than lithium ion and sodium ion because we are not using organic electrolytes. And also zinc and air, of course, are very cheap. So not classified currently as a critical raw material by the EU, although you never know when they will bring out the new list. The list gets longer and longer here in the EU. But yeah, for now we are fine. Zinc is very often used. I would say many of you have probably a little zinc planter on your balcony or something. So if it is cheap enough to make a planter out of it, I cannot imagine that it's too expensive for a battery.
So I also was wondering, Jennifer, did we answer your question well?
Yes.
Yes, absolutely. I was just curious to get some deeper thoughts based on the conversations we had in the MOOC.
Yeah.
Okay.
Yeah, so for also the nice thing about vanadium flow is that there are pilots at the moment. So the biggest one is in China right now. So they are building or they have built the first one. And I think it was like almost it's more than 1 megawatt hour. I cannot remember it. And but for sodium ion, we do not have such cells yet. So I would say that we also, for a very fair comparison, we will need to wait for sodium ion to become really big, and then we can do a real safety assessment for both. Oh, there are more questions in the chat. From Ali. Hi, I'm Ali. I am excited to participate in this webinar. I'm very curious about sodium-ion batteries and especially interested in the latest updates on their modeling and simulation approaches, both globally and in Europe. I'm also a new PhD student in electrical engineering and very interested in developing my research in the battery field. Since my background is not in chemistry, I tend to understand batteries more through physical models and equations. If you have any advice regarding pursuing research in this area during my PhD, I would be truly honored to hear it. Well, Erik and we have another friend, Anish, and Anish works as a PhD student with us on the Resilient project. And I would say you almost sound like Anish. Anish also thinks a lot through equations and through flows and through Nernst equations. While I tend to personally really think about the whole system in terms of molecules moving around. And what really helps us to understand each other is to just talk to each other. And yeah, so yesterday we had a moment where we both identified the same issue in our research project that we have to overcome. But we had that from different angles, and it took us 15 minutes to realize that we were actually talking about the same thing. So I don't know if you have, if in the group that you work in now, you have people who have a very strong chemistry background. I would say just talk to them. And then if you find a paper or you have a problem in your own research, just go to them and then ask for their opinion. And then you give your opinion. And because it's not like you have to learn only from them, I would say they can also learn a lot from you because thinking in physical models and equations is very, very useful. Because when you think in models and physical models and equations, you can really fully understand and predict what's happening. But in chemistry, the thinking is generally more in terms of this happens, then that happens, then that happens. And that is very nice for looking around and identifying things, but it's not so good at finding real issues and real correlation. So I would say that both can learn from each other. But this is a problem that we also very often see in our own battery group. We have physicists, we have chemists, we have electrical engineers, and they all speak different languages. And when they have to work together, it can sometimes be a little messy. But I would advise you to just talk to the other people in your group. Does that answer your question?
Yes, thank you so much.
Okay.
Yeah, there was also another question from Ali about the work on sodium
Oh yeah, I
batteries.
forgot that.
Yeah, it doesn't matter. I dropped a message in the chat where they recently gave some information on the latest sodium-ion battery from China. It's an interesting part. But roughly saying, as I mentioned earlier, sodium-ion batteries looks quite similar to lithium-ion batteries, but for the positive electrodes, there are currently, say, 3 paths. That is the one that uses the same kind of layered structures as being used in the lithium-ion battery based on NMC. They all, of course, modify it so sodium can easily come in and out. That's one part that is basically analyzed by the Faraday Institute in the UK. Then you have Invertor, that is a battery company in Dunkirk in France. As far as I'm concerned, they work with a positive electrode based on vanadium oxides, etc.
Yeah.
The complete structure I do not know. It's partly secret, but you can find it in some papers how it should look like. And then you have the Chinese pathway, and they basically work with Prussian blue relatives. So that's all based on iron cyanates with all kinds of different compositions.
I would say that's my favorite one. I think that's also your favorite one, right?
Yeah.
Yeah, because it's just iron. I think every country on earth should find the resources for that battery in their soil. So that's really nice.
So
Yeah.
then we also got a remark from Tiago, but there is not a specific question. So
let me read it.
Yeah.
Hi, my name is Tiago Dans, and I'm Brazilian living in Estonia. That's quite a move. I work with recycling of polymers from construction, and last month we were trying to develop a new material based in these materials. I am interested in SPA, that's PVA phosphoric acid, polystyrene sulfuric acid. So
solid
that's
polymer electrode, isn't that, or what is it? SPE?
Yeah, that's a solid electrolyte. Yes. Oh, that's very interesting. We also work in Delft on solid electrolytes. Erik and I are not working on that personally, but of course we see a lot of these people. And then you are working on PVA with phosphoric acid, so that's and polystyrene sulfuric acid. That already looks a little bit like Nafion. And this is for a lithium-ion battery. I would say so, right? It has to be sodium. I'm studying about it, yes. Well, very interesting.
Yeah. Well, we can say in this MOOC there is not so much going on these polymers, because that is a completely different story. And of course we cannot cover everything, but obviously polymers are an important material in any kind of a device. So in lithium-ion batteries, it is indeed used as a membrane, as a porous filter, to make sure that you can have your liquid electrolyte dispersed in that. And then one of these materials can for sure be of interest, and a cheap membrane based on this kind of polymers is very much welcome, because today it's almost used via a system that uses a lot of fluorine, PVDF, etc. And of course, in the future, we would like to move away from that.
Yeah, but also a solid electrolyte is also works the same. It has to apply the same chemical and physical principles still have to apply. So although we don't talk about them specifically because they are quite niche, I would say I think it's module 4 where we will talk a little bit about electrolytes and the layers that can form on electrodes and stuff like that. But for solid electrolytes, what I mainly always hear from the people in our group is that the polymeric are tend to be a little bit softer, and that's why some people do not like them because they want to use these electrolytes to stop dendrite formation of lithium. I think we talked about that in module 2, but yeah, they are not strong enough to do that. So then people move to ceramic electrolytes, but they have a very low conductivity. So I don't know about this specific combination. To me, I don't think they sound to me so strong. So I don't know what will happen there. But yeah, you also say that you're doping this material.
Yeah, what I can say about the polymer electrolytes, basically they are divided in 2 different units. That is one polyelectrolyte. That is basically an electrolyte where the polymer is being ionized. And then you have the kind of a gel polymer where you have a polymer where a lithium salt or a sodium salt, depending on what battery you're looking for, is being dispersed. And then there will be used a plasticizer, that is another organic solvent in very low concentrations, so it stays a gel, and the salt is then ionized and make sure that you have lithium or sodium conduction. But for the polyelectrolytes, it's basically a lithium polymer salt. Does
Yeah.
that answer your question, Ali, or Tiago?
Yeah, if you have more questions, let us know. Maybe we just move on to the next question, then we come back to the solid electrolyte discussion. So regarding battery simulations, which software do you personally prefer or recommend for sodium-ion battery modeling? My professors are quite interested in using COMSOL. What is your opinion about its strengths and limitations for this purpose? So in our group, we do, though Erik and I do not do this ourselves, but we do modeling, and for that we also use COMSOL. Yeah, so I do not know whether that is for sure the best, but the people that work with it are always very hyped. But there are a lot of good things about COMSOL, and things that people also do in our group is a lot of Lattice-Boltzmann LBM methods. So that's what they use. Do you know
Yeah,
why
there are-
COMSOL is so great, Erik?
Yeah, well, COMSOL is a commercial product that is quite often used by many other in the industries because it's easy to implement.
And you can also,
And
yeah, it's very easy to share as well.
it is very customer friendly. But we also use Python, and Python is a free software that you can use. That has basically been developed actually in Delft, but it's free. And other people are using MATLAB Simulink. And the advantage of MATLAB Simulink is that it is student friendly, and the way how the codes are easily imported in COMSOL. That is what I understood. So as soon as you have your model created in MATLAB Simulink, you can easily transfer it into COMSOL. But how that goes, don't ask me. That is what I heard. But the more advanced system is Python, because that can basically do everything, or Julia. And I'm not familiar with Julia, but that is a new system that is basically used in Scandinavia. But these software projects programs are available. But if you ask me, I would certainly say try always Python, because most people of PhDs, etc., are using Python, and that is so common that you can communicate with your PhD colleagues.
Yeah, but it's also nice to also do things that your other colleague PhD students are using. Yeah, because Anis uses it a lot, and then yeah, he uses it because his colleagues are using it. So that's the reason why. And they publish papers, so then you know you have a guaranteed success. So maybe we can move on to the next question. So Ali, if you have a follow-up question, let us know. So Pascal said, I'm wondering how far can we expect the current lithium-ion batteries or sodium for electric vehicles to become more efficient in volume mass with technology development? Well, Erik and I discussed this a lot because we work together with the solid electrolyte people, and they always claim in their presentation at the beginning, we are working on the 1,000 kilometer car. And I don't own a car, so I'm not very interested in that. But I also feel that if your car can go 500 or 600, that is already good enough. That's what I hear people say who have an electric car. And you also see industry is not really moving forward towards solid electrolytes. I don't know why. They probably know it better. It probably doesn't work so well for them. So what you see is the chemistries that we have now. They are, of course, we have NMC that's now really growing. But if you look at lithium iron phosphate at LFP, then you really see that the way that they engineer the battery, so they have very thin layers of electrodes and very thin layers of electrolyte, so that the ion exchange can go so quick that from the same chemistry you can make something that is much more efficient. And I think personally that will grow. I do not really see lithium ion batteries double in efficiency, right, Erik?
No, well, you have to realize, and that is a back of the envelope calculation. If you see what the active components are in the battery and what the percentage of inactive components are in the battery, then say it is 50% active and 50% inactive. The inactive part can be reduced, but not so much. So that means even if you find better materials, then still you cannot double the overall capacity because you still need to have an enormous amount of inactive material like casing, current collectors, membranes, etc., electrolyte. So you can optimize it, but going down to 25% of inactive material would be enormously great.
This is also how Tesla beat a lot of its competition when they introduced their LFP battery-powered vehicle, right? Because then for the LFP battery, you need a lot less safety measures because it's a much safer battery. Yeah, personally, I think that for the high-end car market, we already have the batteries that we need. But let's be real, most people on the planet are not going to drive a high-end car. So yeah, maybe for these people or for some other specialty purposes, we will need that. But especially price-wise, I think is much more interesting. So LFP is already relatively cheap, still has great energy density. But yeah, I'm really excited for what sodium-ion batteries will bring to the EV market.
Yeah, there is still competition between the sodium ion and lithium ion, not only here in Europe, the US and Africa, wherever, but also in China, and that is very interesting to follow that. And what you see is that the sodium ion batteries starts to revive, and then probably there will be a revival again from the lithium ion based on lithium iron phosphate, etc. So it's for you very interesting to follow what happens, particularly in China, because these people, they know exactly how to optimize these systems. Rather than to come up with new chemistry, they optimize it in a better way, so they can then improve the energy density without going into new chemistries.
Yeah, there was somebody who made a very interesting point about all of this in the discussions that I all of a sudden cannot find anymore. But they brought up a link to a to an article. So the question, this was the discussion about where we ask you, when do you think there will be large scale implementation of sodium ion batteries? And then somebody said, maybe I can share my screen so we can all read it in the same time, if I can. Okay. Share. Yeah, so somebody said, in my view, the usual R&D to commercialization cycle applies, but adoption is also shaped by market dynamics. For the next generation of EVs, LFP looks like a safer bet. It already meets key performance needs. Its cost curve is still trending down steeply, and production is heavily scaled in China. With the current focus on production affordability, mass market cars, this chemistry will likely remain dominant in the near term. I think that is a very interesting take. Sodium ion could gain traction if it manages to undercut LFP in cost. At that point, we may see implementation, testing, and scaling in earnest. Personally, I don't expect that to happen within the next 3 to 5 years. So I think this is a very interesting take because many people, including me, we are super excited about sodium ion, especially because of price, but also because of sustainability and the critical materials. But I cannot disagree with the statement where you see that this will only start to happen when sodium ion is cheap, and that can only happen when it is already mass produced. So there might be an issue there in a very competitive market for sodium ion to get into that. So yeah, price wise, let's see what happens. But the first cars have already been announced with sodium ion batteries. So some companies are betting very big on it. I don't know who gave that comment, but I think it was a great comment. Are there more questions, comments, things to discuss?
Thiago has a question, or at least a remark.
I cannot see that.
That's the PVA and phosphoric acid-based membrane is actually solid due to the cross-linking reaction. What I'm testing here is a mixture of polystyrene and sulfuric acid and PVA with phosphoric acid. Separated, one is solid and the other is pasty. Together they form a gel with better conductivity and new characteristics. I was really excited about the results, and that's what brought me here. Theoretically, proton membrane 4H plus proton conduction. So I think, yes, that's for sure interesting for the old-fashioned lead acid batteries, but also, of course, for the vanadium redox flow systems, because the Nafion, which is being used today in most of these proton conductor batteries, is expensive, and the production, how this is being made, is nasty. So if we can replace that by any other membrane, and you're talking about a solid membrane, then hopefully it is so solid that vanadium ions cannot really go through it, so the crossover is minimized.
Very interesting. But you also worked on a proton exchange membrane, right, Erik?
Well, we do that here in the group, proton exchange, we do that. I do not see that this could be in a single membrane as a proton exchange. You need to have a double membrane, so you have to find a double layer on this part. But it can certainly help if we find some OH- conductor that can be used in combination with such a system as described here by Thiago.
Sorry to interrupt. Actually, now we are making lab tests about this material, and maybe we can share the results with you. And why not to collaborate with this development? I think we can have very good results in this sense, because we really are taking things from construction sector and trying to make upcycling with this material. And we think we can maybe use this material like a polystyrene, expanded polystyrene to make material for electronics and make resistors and maybe capacitors and things like this.
Sounds
Yeah.
great. So
Yes, send us an email, I would say.
yeah, with short information, make sure that you do not disclose confidential information because we don't want to run into these kind of issues. And then sure, we will share it with our colleagues and see whether we can use this. And you never know how we can set up a collaboration.
There was
So
another
thank you,
comment.
thank you very much. Yeah.
You're welcome.
There was another comment from Ali. Many discussions focus on whether sodium-ion batteries could replace LFP, but do you think sodium-ion could also become a good alternative to lead-acid batteries, especially in large-scale or low-cost applications? In countries like Iran, lead-acid is still widely used and very expensive.
Inexpensive.
Well, I know that Erik has a very big opinion about using lead-acid batteries as for large-scale storage. So maybe you can talk a little bit about that?
Yeah, Miss. One of the big advantages of lead acid, as long as you have enough space and enough room, etc., for everything, and weight of the battery is not an issue. Why not using an inexpensive system that you can use and recycle? The advantage of lead acid is that they can today almost for 100% recycled. For the sodium-ion battery, that is for sure not the case yet. It will come, but it's not there. So if you can really use an inexpensive lead-acid battery compared to a more expensive sodium-ion battery, then why should you change a winning team? So I'm in that respect quite in fond of lead acids. You can recycle it. It is cheap and abundantly available. And probably in the Western countries, people move more and more away from lead acid. So probably other producers are very happy that they can still sell the product.
Yeah, and safety-wise, I would say it's very similar to vanadium redox flow because it's also a sulfuric acid. Lead is also, you should not dump it in the ground. So
exactly.
Yeah,
and
I find it stupid that we don't, but like here in the Netherlands, there's a big thing against lead. Understandable, of course, but to then also push it away from these energy storage systems, I think is really stupid, personally.
But you can recycle it, so I think it is absolutely great to use that.
Yeah. And I also know about but that's something I cannot give all the details because I don't remember, but there is a company in Australia who is working on, I think it's bromine something battery, and they repurpose lead acid producing and recycling facilities, and they can then produce, and it's really in the same packaging, they can produce another type of battery. I will search it up later. That that then has a higher energy density, very similar safety profile, and you can also recycle it 100%. Yeah, but sodium-ion batteries, for low cost application, I don't see that happening in the next 5 years. So if I were now, this was for countries like Iran, I would say go for lead acid and then see when that breaks down, you will just buy the sodium-ion batteries. We have a comment from Doto. What are the main environmental challenges associated with the large-scale production of lithium-ion batteries? That's a very interesting one because it's a very, I would say, it's a little bit unclear how some factories are producing their lithium-ion batteries.
Well, it's not only producing; it's the whole chain, of course.
And mining.
The carbon footprint, etc. So if you look at, for instance, how today the cobalt is being mined, that is not in the most nicest way. So that also should be taken into account. How are we going to mine it? And that is certainly something the EU has been decided that we do not want to have these materials from countries that do not respect people working with a good working environment. So no children who are going to mine, etc. So that means in Europe we limit our resources by that. You can question that. I'm not a politician, but I can understand that these decisions are being made. So if you talk about environmental challenges, if you look at how the mining is of cobalt in, for instance, the Democratic Republic of Congo, you can imagine that it has an enormous impact on the environment. The same could be thought about, what do we do with the lithium? If you see lithium is being taken from resources in the Andes, in Latin America, in South America, but also from Australia. But in the salt lakes in Chile and in Bolivia, you see really a lot of these salt lakes. And what happens if we take lithium from there? Do we spoil it or not? These things we have to consider. So it has an environmental impact, but that is the mining. And then what happens after we have the battery if we need to recycle it? At the moment, we do not have a complete recycling system available for all the components that are in the battery. So there are companies who put everything in a smelter. So then they only take out the precious materials like the nickel, copper, manganese, cobalt, but the rest is gone, and that will be put in ashes, etc. And basically it's downcycling, so it's not really recycling. And what do we do with the residuals? So what is that? Does it have an impact on the environment? Good question. So again, what I was saying in the beginning, we do this course for everybody who is interested in battery technology and can help us to improve everything. So recycling is very important. Mining is an important issue. So if someone of you can find ideas how to do that better, that would be great for everybody.
Yeah, I also read recently that there are some pilots in Chile where they really try to involve the local community. And I don't remember specifically how they did that, but I remember that the people were quite okay with it. And that's always the case when you do a lot of these industrial processes. You need to make sure that the people that live close by are not dying because of diseases because of your process, but that they co-benefit in it. And also, if you keep an eye on them and on their feedback, then you can also close these loopholes of pollution and everything. And I think they were doing that quite well in Chile, but yeah, the Democratic Republic of the Congo, that's just horrible what happens there. So yeah, I fully understand when that people are sometimes a little bit hesitant to then use a battery based on cobalt oxide. And that's also a way to limit yourself. You can limit yourself by choosing other battery chemistries. So if you are going to buy a car and you can check different battery chemistries because for lithium ion, because we have talked about that in this MOOC, then you just go and check where do these minerals come from. And I think it will be module 3 or 4 where we talk about where some of these key elements come
Yeah.
from. And then you
And-
can just look it up. How is it now? It's 2032. How are people mining cobalt right now? And if you then see a car battery that has it, then maybe you just go for another car. That's also another way to do that. Car manufacturers are very hesitant in disclosing what type of battery they have. But within, I think, 1 or 2 years, there will be the EU battery passport. And then it's mandatory, at least in the EU, to have that. to have the knowledge. And I cannot imagine that if they bring out a car here in Europe, that they will use a different battery in Australia. So then you can use that information, I would say.
Yeah, exactly. In one of these courses, I also go into what life cycle analysis there will be and what the consequences on the product. And of course, companies are not really willing to disclose completely what the system is about, but the EU has at least find a solution for that. So there are rules for them how you describe your product. And you will find it in the module how all these things will be called. And these are typically written down in some documents that I cannot go into detail today, but these documents are open to the public, so you can really understand what is necessary for companies to describe. So people who are buying a system can really see, okay, this is what I want and that is what I don't want.
Very interesting. Somebody said, I do part-time volunteering with UK Energy Storage non-profit, and we still use lead acid batteries for the setup. Yeah, that's great. And you also see some of these YouTubers that then try to fully live off grid, and they also very often will use lead acid as like the backup for their lithium-ion battery storage. So then because not a lot of lead acid batteries cannot deliver a lot of power at one point, if you still then need to use your water kettle, then you just use your lithium-ion battery, and that is then constantly charged with your lead acid battery. Maybe you can check out these videos, but really cool that they still use that in the UK. And then Eric said, I was listening to a podcast the other day where the guest mentioned that sodium-ion batteries were for a problem with lithium-ion that no longer exists. I didn't catch what problem the guest was referring to, imagining he didn't mean price and probably not environmental concerns. Can I assume it would be increasingly lower safety risk associated with lithium-ion? Would this make sense? And then we will move to the other question. I think it is the price. I think it really is the price, and I also think it's the critical materials, because before we had LFP, then we really needed to use nickel and cobalt, which you don't have to do now anymore. And I would say what we just discussed is that sodium-ion batteries are can have a lot of problem, a lot of competition from LFP. One thing that sodium-ion batteries might have that I read about is a much better temperature range in which they can operate.
Yeah.
So for starting cars, and maybe then in some very cold environments like Russia, northern Canada, maybe in those places they will be really nice.
Exactly. That is what you see in the link that I showed you earlier in the chat. So the company there mentioned that the battery might work at -40°C. So, and that is certainly an issue with lithium ion, because the conductivity of lithium ions in these electrolytes becomes so worse that most likely it looks like the battery dies. The power performance for a lithium ion battery is basically best between -5 and 40°C. And
I think one of
sodium ions
these,
are better.
yeah, I think one of the Chinese companies, what I read was that it could go to -30 even. That's really nice if that is really true. But companies tend to lie about these things, I would say. And also, not a question, just a comment. I neither work nor have a background in science or any kind rather. I'm a translator, Spanish English, and have become fascinated by renewables and energy transition since starting the work with the energy sector clients some years ago. Courses like these and also conversations like in this webinar are a great way for me to get a better handle on what goes on behind the text I translate and the articles I read. Thanks, everyone. Well, thank you very much. I saw you on the world map. I think you were. It was one of the Spanish islands, I think, if I remember correctly. It can also be somewhere else, but thank you so much. Are there some good solutions on Ono Cafe, Michael? Are there good solutions for lead acid batteries in use in cold seasons, winter, etc.?
No,
No,
No.
yes.
No.
Sorry. Maybe wait there
si-
for the
sim-
sodium.
No, simply the electrolyte freezes. And the only way how people are dealing with that, and that is what you see in Canada, in all the garages, people have their own heating mat. So the battery will be kept on a certain temperature. But
Yeah, there's also the city in Russia where they never shut off their cars, I read.
so there is no real solution other than make sure that the electrolyte doesn't freeze.
Oh, and then somebody said, Thiago says Estonia minus
Yeah.
27 degrees in the winter. Well, I will not be going to Estonia. So thank you
In the
so much
winter.
for, yeah, thank you. Yeah, in the winter, of course.
I
So
was
thank you
there in the
so much.
summer, brilliant.
Okay.
So I will go back there, but not in the winter probably.
Yeah, Erik and I work together with a lot of the people in Scandinavia. And now I'm always fearful that they will invite me for some meeting in the winter to Norway or whatever. So, but that didn't happen so far. So let's hope that that it will be a summer meeting. Hello, everyone. I'm Ika, if I say that correctly, Rahim, a recent graduate in chemistry from the University of Turbat, Pakistan. My bachelor thesis research focused on microbial fuel cells. Okay, that's very interesting. Specifically fabricated a proton exchange membrane. I'm interested to work on sodium-ion battery in future. Currently, I'm exploring opportunities to enhance my knowledge, sodium-ion battery researcher. I'm eager to pursue a master degrees abroad, and I am actively seeking international scholarships to further enhance my academic and personal growth. That's very interesting. A microbial fuel cell. I think I've seen that one time at a conference. I think it has something to do with where you use the proton exchange membrane of the, now you use the proton pump of the cell to then change the concentration. Very interesting. Yeah, I would say scholarships. I never got a scholarship. It's not really a thing in Europe so much, but I would say Erasmus Plus. Right, Erik?
Yeah, you can try to do that scholarship, but you can also ask for a battery unit like MESC. That is a Erasmus Mundus program that is being offered by the University of Picardie in Amiens in France. I will write down here.
Yeah.
I
Great.
think it's MEX.
Yeah, but I would say there are a lot of people. Yeah, we are only familiar with European European scholarships, I would say. But so if you want to come to Europe, but yeah, I would say sodium-ion batteries at the moment, that's everywhere. So while Erik is writing in the chat, oh, the Spanish island was Mallorca, so that's I was correct there. And
Oh
companies.
yeah, I put it in the chat. I think it's called MESC or MEX. I forget, but that doesn't matter. It
Oh,
is
you
an
have to. Oh, Erik, you have
it
to
is
put
an
it to
Erasmus
everyone,
Mundus.
by the way, because we
Sorry?
cannot see. You have to put the chat to everyone because
Oh.
we cannot see the chat.
Sorry.
MESC Plus.
Yes.
So yeah, good luck with finding a scholarship, I would say. So companies like CATL have claimed to produce sodium-ion batteries with performance very close to LFP. I was wondering if you have personally seen such batteries or tested their output characteristic in the lab. Personally, I find these reported specifications very interesting, but I haven't had access to such cells myself to verify whether these claims are accurate. Now, I was at a conference, I would say this was 2 years ago, and then somebody said to me in a presentation, well, sodium-ion batteries are coming. And before that, I always heard sodium-ion batteries are never coming. So I was very interested, and then that person said, yeah, you can already order them on AliExpress. So then after that presentation, I went to AliExpress, and then I bought some. I donated them to the group because I personally did not have the time to look into that. Nobody used that. So I don't know if they are from, I could not see from which company that was. What I see online is that it is very hard to already get these batteries that are very well marketed by these companies. And I personally always take these specifications with a grain of salt. I cannot imagine that if they now start making sodium-ion batteries, that they are already almost as good as LFP. Do you agree with that, Erik? I cannot believe that.
Yeah. Yeah.
So yeah, let's see when they come to the market, because car manufacturers, I think it was a combination of Volkswagen and the Chinese car manufacturer. They are going to bring out a sodium-ion battery car. So if the specifications are true, we will see it in the car. And I think that's scheduled for the end of 2026. So let's see whether they can deliver on that. But until I see it, I don't believe it. But personally, when I see a battery that performs like 80 or 75% of LFP, then I think we are there for sodium-ion batteries. Then Thiago made a comment: lead battery suffers from KC problem in winter, more cold, less reaction. What's KC again?
Kickstart, I think. Is that true?
Kickstart problem.
Coefficient of solubility when it's more cold, less reaction, less ion disponible to make reaction.
Oh yeah, and somebody also gave it a clap, so they also agree. Oh yeah, today's yeah. Oh, somebody posted the website for the scholarships. Yeah, we'll see whether it this type of battery can save Volkswagen, right? I'm not German, so I don't care for it. But it's yeah, it's very difficult to see that car manufacturers in Europe, like here in the Netherlands, the adoption of electric vehicles is very big because of some tax incentives, but also people who then make the switch, they really say that these cars are more comfortable to drive. But it really is stuck now at the high-end market, and there are not enough models for, I would say, normal people to to just get that. And of course, most people here buy second-hand cars, or like the fifth-hand car. So the second-hand market is quite large, but the electric vehicles also don't seem to really go there, because the electric vehicles they still have a lot of their value when you resell them. So the drop in price is not as huge, and therefore we do not really see adoption by normal working class people to buy these cars. And Volkswagen is of course famous for doing that. When was that? Like 40, 50, 60 years ago, to bring the normal car to the normal people. So well, we'll see whether they can get it through. This is actually a reason why I like sodium-ion battery, because I see this as the electric car for most of the people in the world at the end. I do not think that people who are just having a normal job can afford to buy at the moment the lithium-ion battery car that can drive 500 kilometers. So that range needs to come down. So I would say 300 would be very reasonable, and then have a sodium-ion battery there. Very interesting discussion. We are ending the end of the hour. If there are more questions, I can stay here. If there are more comments, maybe. Yeah, thank you also for the nice meeting. This is the first time we're doing this, so.
Yeah, thank you.
Yeah, if there are no more questions, and we have recorded this, so in a few days it will also be online. And if you have remaining questions, just post them in the discussions. There was one person who posted a proposal that I still have to look at together with Erik, but that will come later. But thank you so much for being here.
Yep, thank
And
you.
then, yeah, if there are no more questions, then we will end the webinar here.
And enjoy the MOOC further up.
So, bye.
Okay,
Bye
bye.
bye.